Well, good afternoon, everyone. My name's Carl Larson from RMCG, and welcome to today's webinar, Compost Calculator, Knowing the Value of Organic Amendments in Your Vegetable Nutrition Program in Victoria. We're really excited to run this session today to give an update on a really exciting research project, and secondly, allowing that connection into the grower and agronomist community within Victoria specifically, and feeding back some really interesting trial results. So just briefly, this webinar is being delivered by VegNet, or the National Vegetable Extension Network here in Victoria, which is one of 10 projects being delivered around the country, connecting growers to research and helping with that translation onto farm. And today's session, we're really lucky to be joined by some fantastic guest speakers from around the country. And I know there's about 40 of us in the audience joining from Victoria and interstate and even overseas as well. So thank you for coming along. We've got Associate Professor David Rowlings from the University of Technology in Queensland, who's going to set the scene around organic amendments more broadly and what the project is looking at. And we're then going to hand over to Professor Ian Porter from La Trobe University on the international significance, particularly around nitrous oxide and nitrogen, before hearing some Victorian trial site updates and an overview of the findings from David Richards and Dr. Scott Matner from La Trobe as well. So before we get stuck into the detail, it's always really handy on these sessions, and I'm sure, particularly in Victoria, given the current lockdown that is thankfully about to end at midnight tonight, it's great to get an understanding of who's on the line. We've just got a couple of quick questions that we wanted to put to you to get an understanding of where everyone's up to and your level of understanding. So there's a little quick poll that's just come up onto your screens that asks a question: do you use organic amendments on your farm, and what types do you use? Feel free to click any or multiple options there, and I can share some results back with us just to give us an understanding of where use is up to amongst us. So we've got about half of the audience that's voted so far, so I'll let people click through and select a response. And we've got about 3/4 of us now that have voted in that. So thank you. I'll close that and share back the results with you. So we've got about, half of us on the line using animal manure, either composted, uncomposted or pelletized, and quite a large proportion using composted green wastes. Over a third using none, which is really interesting. So just one other quick one I wanted to launch with everyone as well was more the method or the how you're using organic amendments. So the options there around incorporation or mulch on the surface. Again, if you wanted to click through and select one or multiple responses there, and I can share back. So everyone, obviously with the hang of this in either GoToWebinar or Zoom or another platform, particularly over the last 12 months. So we've got about 2/3 voted now, which is great. Excellent. So I'll close that and share back just quickly. And responses from the audience here, we can see, a third split. So third incorporating into the soil, a third as a mulch on the soil surface, and then the remaining third not using organic amendments. So nice bit of breadth there. That just helps our panel pitch some of the slides and content at the right level as well. So look, just a little bit of housekeeping too. Thank you for participating in those couple of quick questions. We've got a couple more down the track, but we won't bombard you with everything straight up and let you get into the findings. If it is the first time you've joined a GoToWebinar, you'll see on the control panel just a couple of things I wanted to point out. One is the handouts on the side. So we've got a couple of PDFs there that you can download directly and take away with you for some further reading and reference, which just saves following URLs and trying to write them down. So hopefully you'll find those useful. The second was just the question functions. So feel free throughout the session to type in your questions. They'll come directly to me and I'll put them to the panel at the end of our 3 presentations, and to get a bit of a Q&A going. So without further ado, I'd just like to introduce David Rowlings. So David's going to provide us with a national overview of the project, and David, I'll just share your screen now, so that should be about to come up. And a quick little intro on David. So David's a soil scientist, and his research sits at the intersection of environmental and ag science, so enabling high impact research outcomes that benefit both fields. He specialises in the development and utilisation of improved sensing and monitoring technologies for mitigating environmental greenhouse gases, also improving crop fertiliser use efficiency and monitoring soil carbon. So David, welcome, and over to you.
Thanks a lot, Carl. So yeah, thanks everyone for joining us. So today I'm going to give a bit of an overview, I suppose, leading into the background to this, and particularly around this project that is funding a lot of this research, and really trying to emphasise, I suppose, the current status with sort of across the industry, but also the challenges of using these products. You know, with the end goal of what we are producing at the end of this project, which is this calculator, which Dave and Ian and Scott will be talking about. These are sort of the challenges that are arising in the industry now, and this is sort of where we're heading with this research to overcome these challenges. So the project itself is a national project. It's a pretty large consortium with across Queensland, New South Wales, Victoria. We also have sites in the Northern Territory and South Australia. It's cross-industry, so we're looking at a range of agricultural industries, obviously intensive horticulture down in Victoria, but we also have dryland cropping and dairy up in Queensland, some beef grazing pastures as well, and irrigated cotton down in the Riverina in New South Wales. So you know, a lot of the processes that govern the things we're looking at here are pretty generic. They're pretty universal. So we're sort of taking a cross-industry approach to try and tackle it from a whole range of different products, which basically form these organic soil amendments. So yeah, this funded through the Australian Government's National Land Care Program with input from Meat and Livestock Australia, as well as a range of local bodies. So one of the key emphasis that we're looking at in this project is nitrogen. So it's not the only nutrient, of course, in organic amendments. It's certainly not the reason why most farmers put on organic amendments, but it's one that's often forgotten. And that's why we're sort of focusing on it, because what we really want to try and highlight is how important nitrogen is in these products, and it is actually a very valuable nutrient source that can be used in a effective way. And the problem is that there's some challenges around that, which I'll get to. But we all know that nitrogen is important for crop growth. I mean, study after study, and sort of every single crop anywhere in the world, basically grown on a commercial basis, requires nitrogen. And that's basically led to what is essentially this increase in nitrogen demand, and basically nitrogen fertilizer input. So as you know, agricultural demand and food production demand through global population pressures has increased, the input of nitrogen fertilizer has also increased on a global basis, but also as every single industry in Australia as well. But at the same time, as we're increasing our nitrogen inputs, how much nitrogen actually ends up in the crop, so what we call the nitrogen use efficiency, is actually declining. And this is a function of how complicated this nutrient is in the system, and also how easily it's lost from the system. And when it's lost from the system, whether it's a vegetable field in Victoria or a cotton farm in the Riverina, it basically has these environmental impacts, and some of those will be discussed later. But it's a key issue for agricultural communities going forward worldwide, is how do we actually maintain this production with this important nutrient, while at the same time reducing our environmental footprint. So with that in mind, sort of, we have this fantastic resource in Australia, these organic amendments. So not even looking at the sort of the urban derived compost and the residue side of things, just looking at the animal industry alone, we're producing over 3 million tonnes a year of basically organic amendments, containing over 246,000 tonnes of nitrogen, plus phosphorus, plus potassium, with an estimated value of over $2 billion. So a lot of this is being used already, but it's not being used efficiently. There's issues with basically how we use it, knowing how to use it properly, and actually getting the distribution of it to our where it needs to be. And this is largely because it's highly centralized. So we have these huge operations, many tens of thousands of head cattle feedlots, big poultry operations. So we have this huge concentration of nutrients in certain areas. And that means that transport is a major cost. And if you're going anywhere sort of circa 150 kilometres or more, particularly in the sort of lower intensive industries such as grain cropping and extensive pastures, it really starts to become uneconomical to transport in its raw form. There's a wide range of costs for these products. So you're looking at, ranging from $12 per tonne for raw feedlot manure to almost over $90 a tonne for some composts. Typically, however, if you just sum up the nutrients and potential things like liming value of these products, it is basically cost neutral. And the biggest cost comes down to that transport cost. So how far are you from the source? It's largely going to determine whether it's profitable or not. However, there's big issues with storage and processing. In Australia, we're the only developed country in the world where it's largely unregulated. And that also includes not only the handling aspect of it, but also when we apply it to the fields. And the biggest issue with these products is just the consistency. So what's the big issue? So why are we focusing on this? And remember, we're comparing this to our conventional fertilizer, which is what comes out of a bag, which is relatively easily available. It's the numbers that are basically how much nutrients are in there are written on the bag, and it's quite easy to understand how that's going to get to your crop. So when we start talking about organic amendments, we're talking about this large, diverse range of products, which has not only a wide range of different nutrients, but also a wide range of different how it's handled, and that basically what you're buying as a farmer is much more uncertain. So, one of the first issues is basically how that product's been handled. The age, how long it's been sitting out in the weather, whether it was stockpiled, composted, whether it was blended with some sort of carbon source such as sawdust. All these sort of add uncertainties. You can see on the top right graph, we're looking at nitrogen losses. So this is ammonia. We're looking at nitrogen losses from chicken manure. And depending on how it was handled, and this is just 3 different generic treatments, were actually different combinations of sawdust, the amount of nitrogen lost from that product varies greatly. And what that does, that influences basically how much actually ends up going into your fields. So you might be paying for a ton of product, but the amount of nutrient in it actually varies widely. And as you can see down in this bottom right-hand corner, looking at basically dairy manure and the history of that, and how long it's been stockpiled there for, and how wet it was, really determines the nutrient quality of that product on a per tonne basis. Next question is, well, how much do we apply, and how do we actually incorporate this into our farm nutrient budgets? So multiple different people have different ways of applying organic amendments. There's no real clear or easy strategy across the board, but one of the ways we look at it is basically applying it on a per phosphorus basis. So in this case, we have a crop, it needs 70 kilos of phosphorus. Okay, if we try and apply it basically based on a crop phosphorus basis, we're looking at urban derived compost, feedlot manure, and composted chicken manure. Then you can see for a start, just the application rate, and that top line there is humongous on the urban derived compost versus the chicken manure. So already we've got this vast range of different amounts we need to apply looking at these different products. If we then look at how that lines up with our other nutrients, and so for nitrogen particularly, we want to hit say 300 kilograms of nitrogen. So in the urban derived compost, to get that much phosphorus, we're actually adding too much nitrogen, whereas in the feedlot and the chicken manure, to get that much phosphorus, we're actually under applying nitrogen. So even though these products are very, very valuable sources of nutrients, they're often imbalanced to what we actually need on our farm nutrient budgets. So how do we actually go about trying to get that balance right? The easiest thing in what a lot of happens currently in the industry, unfortunately, is they just ignore the nitrogen and just apply it for the phosphorus. And that sort of leads to other issues as well. When you start to account for, well, is this economically viable? You need to account for all those nutrients that go in there. So we're adding a lot of potassium, but that potassium's often out of whack as well. So even though it's not toxic and it doesn't go into the environment, you're not getting the dollar benefit that you should by the potassium as well. And then the next question is, well, how much of that product actually gets into my crop? And so when we talk about nitrogen particularly, we want to get available nitrogen to the crop, because a lot of it's organic, it's tied up, and it's not available for the plants. So if we're actually looking at, okay, I want to supply my crop with, so in this case, 35 kilograms of nitrogen, you need to add vastly different amounts of these products to actually get that initial supply as well. So actually figuring out how much to apply to get these nutrient balances right is really, really difficult. And how do we avoid over-fertilization in particular, and particularly of nitrogen? So the next question is then, okay, just because you added the right amount of nitrogen, how much of that is actually available? So if we look at, where our nitrogen comes from in our plant demand, nitrogen plant uptake throughout the season increases with crop growth. And traditionally, we usually have urea, we put on a basal dressing and then a trop dressing a little bit later on, and that's really available straight away. So as soon as you put it on, it's pretty much available. It depletes as it's taken up by the crop and it is lost, but it's pretty much 100% available over a relatively short period of time. The problem with compost is that we then put that on, and you might have a little bit available initially, but the rest of it's sort of just a trickle feed coming through, and the availability of that depends greatly on the product itself, and is widely variable throughout the different products, whether it's composted or raw products, or from urban derived sources, or raw products from animal manures. And then of course, as we keep on applying these products year after year, there's sort of slow trickle feed, because it's a slow release. We have this benefit that actually it does carry over into multiple years. And so eventually, once we get these products into the rotation, we should be able to reduce particularly our nitrogen input to match basically what's being supplied from that long-term supply. But the question is, well, how much of that nitrogen can we reduce? So what we need to do is we need to account for the plant available nitrogen that's released from these organic amendments. We need to get the right balance between organic amendments and chemical fertilizer, because you can't use either or. We really need to look at this as a combination of both. So basically what we have here is our plant demand, again, in the red, and basically in this case we're looking at our organic amendment supply of nitrogen in the black. And as you can see, they don't really match, so we really need our fertilizer to come in on top of that and match that supply. So predicting that blue bit, that how much nitrogen fertilizer, is one of the key things we're trying to do in this project. We don't want to go above that line, because then we're going to have environmental consequences. We don't want to go below it, because then we're going to start to run into yield restrictions, limited nutrients. And so what happens when we do get it wrong? Well, then we get into these environmental losses. There's only a limited amount of nutrients that these plants can take up. Before they're limited by other things such as water or genetic limitations. And so as soon as we go above that limit, our nitrogen nitrogen losses start to increase. And so once we get above our basically maximum yield, if we're still putting in nutrients, we start to lose that nitrogen, particularly into the environment. Leaching is a big one. So basically washed out into the groundwater. If in the Great Barrier Reef catchments, there's big issues around that and water quality of the Great Barrier Reef. And another one is nitrous oxide. And Ian will talk about this a bit more in depth next. But nitrous oxide is a potent greenhouse gas, and it's one of the biggest contributors to the greenhouse gas footprint of particularly the cropping and the horticulture industries. So it's an important one that we don't put on too much nitrogen and produce more of this nitrous oxide. And then of course there's the additional benefits of soil health, increased nitrogen use efficiency, increased water use efficiency, infiltration, pathogens. These are very, very hard to quantify, but these are, once again, if you start looking at the cost benefit analysis of using organic amendments, they need to be quantified. And in some cases, it might not just be increasing soil health, but just improving soil health. So this is a study we did at Gatton. You can see the red line there where we added composted treatment versus raw treatment. We actually maintained our soil carbon. So it didn't really increase, but it maintained versus our raw product, which is where it actually decreased due to the intensive cultivation of that cropping system. So this is a very busy slide. I'll just introduce it very briefly, but this is the overall project. We're a consortium of suppliers, farmers, labs. So we're working with some of the commercial laboratories to make sure that our test results come out in a compatible format, and extension teams to develop this integrated nutrient calculator that works across industries. Basically, we have lab analysis for model parameterization. It's validated in the field and with a feedback cycle for the calibration. So we're sort of hoping to have a generic one that'll work across industries with some tweaks or some specific inputs, particularly around the nutrient budgets. And once again, a key aspect of it is actually how do we get this information across the growers in a relatively straightforward and easy way, and really simple ways that they can compare between products. So you see on the right, we're looking at, okay, how much nitrogen do I get from these different products if I'm putting on urban drive compost versus raw chicken manure, etc. And that's it for me. So I'll hand over to Ian.
Great, thanks, David, and really great to set the scene. A really interesting project and introduction to nutrient budgeting more broadly. Just while Ian's bringing up his slides, I might just do a very brief introduction. So we're really lucky to have Professor Ian Porter from La Trobe join us. During Ian's long career as a research scientist, he's led both Victorian national and international research programs, seeking more sustainable solutions for pest and disease control in agriculture, and also preventing damage to the climate and ozone layer. This has included a number of leadership and research programs to benchmark the sources and scale of greenhouse gases, such as nitrous oxide, carbon dioxide and methane, from horticultural crops in Australia, and also provided mitigation options. Since '97, Ian has led as co-chair the Methyl Bromide Technical Options Committee for the United Nations Montreal Protocol, and that protocol has actually been successful in phasing out 95% of man-made ozone depleting chemicals. So a very fitting segue into Ian's topic, which is going to provide us with the overview of the international significance of the project and its benefit for growers. Ian, welcome.
Yeah, thanks, Carl, and welcome to all the growers, industry reps, etc. out there listening in. So thank you for that. Look, Dave's alluded to the downside, I suppose, of overuse of nitrogen, etc. But what I'm going to do is show you a few drivers that are changing the way we're using fertilizers, inorganic fertilizers, organic products, etc. That are going to be good for industry as a win-win. And because we're in the program trying to develop practices and knowledge that will allow us to move fertilizer management with organics that continues for as long as possible. And so we'll just go through in a very quick time just this way we're doing that. So the drivers I'm going to focus on are mainly the atmospheric, because that's the area that I think that's most unknown. So the points 1 and 2. Nitrate runoff into streams, you've all been are aware of that. Dave mentioned the reefs. But the lesser known stuff is really the impact of nitrous oxide on the climate, but more so the impact of nitrous oxide on the ozone layer. And that's derived from really mismanagement of nitrogen at ground level. And what I put there at the bottom is that this nutrient calculator and the work we're doing can provide industry with a win-win situation for hort industries. And I'll explain that as we go through. So on the right there, you'll see a drawing down N2O. That's a document that's prepared by the United Nations under the Montreal Protocol for its ozone effects, not for its climate effects. Well, it's got both ozone and climate effects in it, but it's not from the global warming. It's mainly from the ozone depletion point of view. And then you've got your EU directives, which came in 1991, looking at nitrate into streams. And that's continued on in Europe, where they have nitrate vulnerable zones that they look at, where they cap the level of nitrate in those streams and in those regions, and they try and get growers to work to those levels. Now they're very low, as you can see on the bottom right, or you may not be able to see, but it says 170 kilos of nitrogen per hectare. And of course, in some of our systems in Southeast Australia, we use a tonne, not 170 kilos. So, but there are ways of reducing our inputs, and this project will help. Just this is Peter Deuter's slide that's been shown to you many, many times before, but just to firstly go into the greenhouse gas. So this is the global warming aspects of the agricultural industries and horticulture. In the middle there, you'll see that it contributed in Australia 75 million tonnes of carbon dioxide equivalents, 14% of the issue. Energy is the big emitter, industrial processes there, land use and waste as well. But in the green box, you'll see that horticulture is 0.42% of the agricultural component. So yes, it's small, but can we do something to improve that and improve the green image of the hort industry? You won't be able to read all the numbers in the table, and that doesn't matter. It just shows you what's available through Peter, Dee, Hal, all the past projects where they've now got the Hort Carbon Info tool, which allows you to get a calculation of your greenhouse gas balance. And on the top there at this particular farm, Peter Deuter ran this last year, I think it was, in Queensland. You can see there that he's got 406 tonnes of CO2 coming from the farm for energy and 133 from nitrogen fertilisation, which includes both the inorganic N applied in fertilisers and the manures that were applied on that farm. And you can see it's roughly 20% of the emission is coming from the nitrogen and the fertilisation. So that's why we need to do something about it and try and improve the nitrogen use efficiency and nutrient use efficiency. So this just summarises that in one slide, just the carbon footprint as it relates to climate change and global warming. The tool is on the greenhouse and agriculture side at the Uni of Melbourne. The sources are, as we've said, approximately 70% for fuel and electricity, 20% for nitrogen fertilisers and manures, and then the rest for waste. Now in Victoria, we use about twice as much fertiliser as some of the regions up north. So maybe it's a little higher than 20% in this region, and so it's really worth focusing on. Now, besides the global warming, this is the unknown part of nitrous oxide. Nitrous oxide emissions, they were at 270 parts per billion. With history, they've risen to 325 if you look on the left-hand side of the page there at the graph. If you then look at the right-hand side, you'll see this increase. It's increasing every year. All the increases in nitrous oxide are due to mankind or person-kind anthropogenic activity. And the sources, agricultural fertilisers are the key source, and the horticulture is the key source is from fertilisers and manures, as we've said. That's in our industry. What's not known is that N2O is also the largest ozone depleting product. All the other products that we've spent 30 years on the Montreal Protocol getting rid of, including methyl bromide on the far right, have all been phased down from the grey historical level to the blue and even further than this in 208. They're much lower now. But nitrous oxide is this large emission on the left, and it's not yet controlled under the Montreal Protocol. If it is, that means that restrictions will come in to phase it out or regulate its use under Montreal. And Montreal is a very effective climate agreement. So this just puts it in perspective with the other gases, the methane that you hear about for global warming. So if you look at nitrous oxide and its contribution to global warming, focus on the bottom of the graph. This is where we are with the phase out of all the halons and the other chemicals, which have both ozone effects and climate effects. And here you can see the increasing nitrous oxide and the errors from the lowest predicted increase to the highest under climate. If you look at the Montreal Protocol, where it's damaging the ozone layer and the implications there, all these other products that we spent 30 years to get rid of have gone to this level now. Look at where nitrous oxide is sitting. It's going to cause, and is causing presently, the biggest concern for ozone layer depletion once these others are phased out later in the century. So what can we do to fix that? So this is not just about doom and gloom and drivers, it's just the drivers that are there. If we work sensibly with these projects and the calculator, we can get there. So we're just going to go into mitigation. So in our past work in the last decade, we've looked at annual nitrogen budgets. This is the breakdown. We're not going through those, but most of the crop takes off about 10 to 20% of the budget of nitrogen. Losses to the atmosphere can be up to 40%. There's lots of variability there in the nitrogen that goes up and the nitrous oxide and the ammonia, but they may be 10%, they may be 80%. But the average in this trial is 40, and then there's some leached to the groundwater. So there's large issues, 80% going somewhere else, not to the crop. So this just gives you a summary of the 1 tonne that we, or half a tonne to 1 tonne of nitrogen we put in southeastern Australia and throughout some other regions in sugarcane, so in northern Australia. Maybe 10 to 50% is emitted, 20% marketed, 30% leached. What can we do about this? So in the past, we've looked at on farm, we've had manures where we've applied enhanced efficiency fertilizers or inhibitors to maintain the nitrogen in the profile. And if you just focus on the right here where the red arrow is and the green arrow, you'll see that from the manures, when they were added, we could get a 10-fold reduction in the amount of emissions of nitrous oxide, and that compared favourably with the same emissions from the inorganic fertiliser programs. So using these in our programs can really add benefit. When we looked at a base fertiliser application of manure with the inhibitors on it, only the base fertiliser, and let it run through to harvest without any side dressings, so we could see the value of that base fertiliser by maintaining the nitrogen in it, we were able to get these larger yields compared to what the grower was doing without it. The normal, the standard out in industry, this was with it. So we're able to actually get a 60% increase in yield, and that translated into a $1,500 to a $6,000 gain in this particular trial from that inhibitor. So just to conclude, and we didn't have time to go into lots of other ways you could do things to the nitrogen to stop the atmospheric emissions and the leaching, excess use and improper timing of application of manures and fertilisers are leading to a waste in nitrogen in the atmosphere, as Dave said. It could be up to 80% of the nitrogen applied that's lost. Methods exist to reduce these emissions, as we've said, and these can return profits to the farm. So this is where the win-win comes in. The inhibitors can be used, pelletization, formulations, we're looking at torrefaction, other methods where we can retain the nitrogen into the product. And I know the industry is focusing on that as well. We've talked about economic returns that can be made, reduced fertiliser labour and number of picks in our case, because we had this gain that came through the nitrogen, but more so that the nutrient calculator is aiming to improve the nutrient use and improving application and timing of fertilisers and manures. And what I'll do is I'll hand over to Dave at the end of this and just show how we can get on the way to the win-win. So just in closing, mitigation of nitrous oxide emissions can dramatically improve fertiliser manure nitrogen use efficiency and also food supply. And I stress again, we look at it as a win-win for industry, ozone and climate. So thanks a lot.
Excellent. Thank you, Ian. And just while I'm handing over to our next presenter, David Richards, I'll just do a very brief introduction of Dave and Scott. So David's an agricultural scientist with an interest in sustainable plant production and greenhouse gas measurement and mitigation. He's got more than 20 years experience in plant pathology in fruit and veg industries and greenhouse gas emission measurement from vegetable production. And joining him is Dr. Scott Mattner, also from La Trobe University. And Scott's a plant scientist with more than 20 years of experience in plant pathology, soil health, plant biostimulants and emissions of climate change gases. He's also the research leader for the Victorian Strawberry Industry Certification Authority in the nursery sector. David, Scott, welcome, and over to you.
Okay, thanks a lot, Carl. Today I'm just going to give a brief overview of the research trials that we've conducted in Victoria with organic amendments in vegetables. So the main purpose of this work is to provide the supporting data for the calculator that Dave spoke about earlier, and also to validate that the calculator is going to work on commercial vegetable farms. So what we're going to go through today is we're going to talk about the 2 trial sites we've used, which differ in their soil types, their crop rotations, and their fertiliser programs. And then we've used 2 different organic amendments at each site, which are chicken manure and green waste compost. And then we're going to talk about the ways that we evaluated the effects of the organic amendments by looking at their effects on crop growth and yield, and then soil nutrients. So again, we're focusing on nitrogen. We also did some monitoring of greenhouse gas emissions. Ian spoke about the importance of that, particularly nitrous oxide, and why we're interested in that. Yes, and so all of the data that we've been generating, together with the other data that's been generated by our project partners and the laboratory studies that have been done by David's group in Queensland. And there's also parallel trials going on in Queensland with vegetables. So all of this we put together to develop the calculator and allow us to evaluate it in commercial vegetable growing. So this is our Werribee South trial site. So this is on the southwest side of Melbourne. So the soil there is a heavy clay. The crops grown at this site were furetto, cauliflower and fennel. So this slide here shows that the crop rotations over the 2 years that we've been running the trials, and it gives you an idea of the fertiliser treatment, which is kind of the standard practice on the farm. So organic amendments are applied pre-plant. So we've used both M stands for the manure, which is a chicken manure, and we've also used a green urban derived green waste compost. So again, the organic amendment's not used every crop, so we can see for the follow-on effects in the following crops where we're not adding the organic amendment. So there's a base NPK dressing applied at planting, and then calcium nitrate side dressings are used later in the season. Now this is our Baxter trial site. So Baxter's in the southeast of Melbourne on the Mornington Peninsula. So we've got a really different soil type down here. It's very sandy. And the crop here is celery, which is their main crop, which is grown over the winter and into spring, and over summer it's cover crop with either maize or sorghum. Now this shows the crop rotation and the fertiliser program used at this site. So again, we're using the chicken manure and the green waste compost as a pre-plant organic amendment. And then here the chemical fertiliser used is really just a nitrogen compound, so it's Kelgran, so it doesn't contain appreciable amounts of phosphorus or potassium. So I'll just go a little bit into the treatments that we used in the trials. So the treatments are really to break the fertiliser program down into its component parts so we can see what each part's contributing to the crop. So this first treatment here, the zero or control treatment, so that's a really important treatment because we need a good baseline to then measure the other treatments against. So we really have to push the system to a point where the crop fails or doesn't grow properly so we can see the effect of adding nutrients on top of that. So we have our organic amendments, so then the other end of the scale, we have our full fertiliser rate treatment here. So this should give us our maximum yield potential. So this is what we want to match with our calculator optimised fertiliser treatments. So we have each organic amendment applied by themselves, and then we have the organic amendments with the full rate of fertiliser, which may be the grower practice on some farms. So that's another standard we want to be able to match the yield of. And then here are our reduced rate programs. So these are our calculated optimised treatments where we've taken account for what we think the availability of the nutrients will be coming from the organic amendments during the cropping period. We've also got a reduced rate of just the inorganic fertiliser as a further comparison. So this shows you the nutrient content of our key nutrients, N, P and K, for the 2 different amendments we've used, our chicken manure and our green waste. So you can see that they're very different, much higher nutrient concentrations of all 3 key nutrients in the manure relative to the green waste. And when we take into account our application rates per hectare, we are getting higher rates with the manure, even though we're using a higher application rate of the compost, the green waste compost, we're still getting higher nutrient applications per hectare with our green waste, with our manure. Now these are total nutrients. So David earlier touched on the fact that most of this isn't available to the plant immediately. So if we look at the mineral nitrogen, this is our nitrate and ammonium. This is just a very small percentage of the total that we're applying. So yeah, the key of the nutrient calculator is going to be to work out what's happening to this organic component of the amendments during the cropping period. So the way we've assessed the effect of the of the organic amendments, so the nutrient effects, is to look at yields at harvest, and this will let us work out any economic benefits. We're looking at biomass accumulation during the season to see how the crops respond to the different nutrient levels in soil, and gives us an idea of how it varies with time. And we've also done a lot of soil measurements of nutrients, and this will let us work out the conversion rate of the organic forms of the nutrients into plant available forms, again, which will be used in the calculator. So we've heard a little bit about greenhouse gas emissions. So yeah, just to underline what was said earlier. So the purpose of this is twofold, really. It's about minimising environmental losses, but it's also agronomic loss of fertiliser. So what's going up to the sky is obviously not there to grow your crop. So we use an automated chamber system. So these were developed by David's group at QUT in Queensland. So they consist of these chambers which sit out in the crop. And during a measurement, the lids will close like that. They'll take air samples at every 15 minutes. They're analysed for gas concentrations. And then at the end of the hour period, then they open up, and then the next set of chambers will shut. So they're operating continuously to give us a really detailed picture of greenhouse gas emissions over the entire growing season. So all these boxes out in the field, they're all connected by sample lines and pneumatic control lines back to this little laboratory, which is on site, and it's got the equipment that with sample valves and air pumps and so on, with online gas detectors, which give us the real-time gas measurements. Now, if we move on to the crop growth, so this is our Baxter site, a celery crop. So here we're looking at the effects of the green waste treatment. So we've got the green waste by itself, and we've got it with our calculator reduced fertiliser program, and as control treatments, we've got our zero nutrient addition, and we've got our full program over here. And we have the green waste by itself. As we move through the season, we can start to see differences in growth between these treatments, and this is close to harvest. So we can see that the zero treatment, the canopy is much smaller, it's lighter green, and over here with our full program, much denser and dark green canopy, and our reduced rate fertiliser treatment from our calculator optimised program is giving us a very similar result to our full fertiliser rate. It's also the same story for chicken manure. Again, we're looking at chicken manure by itself, the reduced rate from our calculator treatment, and compared to the full rate, again, against the zero applied nutrient. As we go through the season, again, we start to see differences in canopy. And again, at harvest, we've got much better growth over here in our full rate, but our calculator optimised treatment is also giving us an equivalent growth. Right, so this is the actual trial site. So we've got 3 rows either side of this central sprinkler line, each with 2 rows of plants. So we'll just do a quick tour of the trial. So you can see there's areas where growth is obviously not as good. We've got paler yellow and much less dense canopy. So over here you can see one of those gas measuring chambers. You've got a nice canopy over here. You've got area of reduced growth here. Over here, another plot where the canopy is not as good, and here too. So if we actually look where some of these treatments fall in relation to these areas which haven't grown as well and the areas that did really well, you can see the zero over here has a less dense canopy. Our organic amendments by themselves, again, they haven't produced the same sort of canopy as our calculator optimised program over here is looking much better. Yeah, just some more plots here. Again, the manure and green waste by themselves have been inadequate to produce the full yield, and much better results with the green waste with the full program. And another one of our calculator optimised treatments, again, looks pretty good and equivalent to a full fertiliser rate. So just actually looking at the actual yield measurements. So here's our zero nutrient treatment. So it's performed poorly, which is exactly what we want to see. Adding the green waste by itself may be a little benefit, but it's still not particularly good. And the manure, which is the higher nutrient organic amendment, has done better, which is what we'd expect. And then we look at our calculator optimized treatment. So this is the manure plus the fertilizer at a reduced rate. There's no statistical difference between that and all of our full rate treatments. Now looking at soil nitrate for the same trial. So here we've got the organic amendments applied out here. Now the gap between planting and organic amendment was quite long in this experiment. So it was about 2 months. So this is largely due to logistics because it's a large farm, and when the machinery's there to put the manure out, it all gets done at once and then it's planted over a period of several months. So we can see our zero treatment has a relatively low level of soil nitrate right through, and green waste doesn't really add much on top of that. But if we look at our manure treatment, it's a completely different story. So we're getting relatively high levels of soil nitrate after application. It is dropping as the season advances. But here at planting, when we're putting a fertilizer on, we've still got a pretty high level of nitrate. So it might be possible to really reduce that fertilizer application or even eliminate it entirely, depending on how much we're getting from our organic amendment. And we can see as we move further into the season, so that the crop's getting bigger, so its demand for nitrogen is increasing, as David talked about earlier. So that's where these latter applications of fertilizer, these are the ones that are much more important when you're using an organic amendment. So you've got much more opportunity to reduce what you're applying up here, and you're probably going to still have to maintain fairly normal levels of application here. And that's what's happening with this other treatment where we've combined the manure with the fertilizer. We're seeing, yeah, we're maintaining the nutrient levels as the crop needs later in the cropping cycle. So in terms of greenhouse gas emissions, so this first one's carbon dioxide. So we're not measuring the entire carbon picture with these boxes because we're not measuring carbon going back into the soil. We're not measuring what's being taken up by the plant biomass. So this is really a measure of what's happening in the soil. It's largely a measure of soil respiration. So after we put the organic amendment on in the manure treatment, we can see we're getting a burst of soil respiration. So we're stimulating the soil biology by adding this organic matter to it. Now, nitrous oxide, this is the next graph here. So this is the one we're interested in terms of both environmental effects, but also losses to the system, because any nitrogen being emitted as nitrous oxide is being lost from the system and is unavailable for the plants. So we can see we get a burst of nitrous oxide after we apply the organic amendment, but we get much larger emission peaks in this system after each addition of fertilizer. So there's a strong interaction between the organic amendment and the fertilizers, which are increasing nitrous oxide emission. So I'll come to this a bit more in the next slide. The last one just shows methane emission. So this one's really not very significant in the vegetable growing system. It's just really centered around zero, quite low numbers either side. It just kind of oscillates around zero. So it's really insignificant in terms of the greenhouse gas emissions of the vegetable growing systems. So this is an earlier trial at the same site. So in this one, we've got the manure with a reduced rate where we've measured the emissions, and we've substantially reduced the nitrous oxide emissions. So we're reducing the losses from the system by just reducing the rate. There's other ways you can do this with other products such as enhanced efficiency fertilizers, which might include nitrification inhibitors, which we've done work in the past which show they can also reduce emissions. There's also liquid nitrification inhibitors which can be applied to organic amendment products, and we have also shown emission benefits with those products. Now I'll just move on to the Werribee South trial site now. So this shows our two sort of extreme ends of the treatment spectrum. So we've got our zero nitrogen treatment, and we're looking at the increasing above ground biomass of a fennel crop. Here we have a full rate of fertilizer. So you can see that they're really different. The growth rate is much reduced at our zero additional fertilizer. Adding the organic amendments in by themselves, we can see that the chicken manure is doing a lot better than the green waste up to a point. But as we go later into the season, when there's more demand for the nutrient, and that's at the time that the nutrient supply from the manure is dropping off, we see the growth rate decrease. Now, if we look at our calculate optimized programs, we've added fertilizer to the organic amendments at a reduced rate compared with a full fertilizer program. We see that they're growing just as well. So that's really good evidence that our calculated treatments will be useful and not going to result in any yield penalties. So here is at harvest, the yield of fennel. I should have pointed out that the inorganic fertilizer rate is up the top here. So we go from no added inorganic fertilizer to our calculator program to the full rate in all of these, the different organic amendments, whether it's chicken manure, green waste across here, or no added organic. So again, our zero added nutrient treatment has pretty much failed, which is what we want to see. Green waste is a bit better. And again, our higher nutrient amendment manure is even better still. And again, same as we saw at the Baxter site in celery, that our calculator optimized treatments are giving us equivalent yield to our commercial full rate programs. So in conclusion, the trial results so far have shown that a calculator which accounts for plant available nutrients and organic amendments can improve nutrient use efficiency. And we've seen that the different amendments differ in their nutrient content and also in their ability to supply nutrients during the season, with chicken manure supplying much more nutrient than green waste compost. So we've demonstrated this potential to reduce fertilizer applications, and especially these early applications when you're using the organic amendments without any yield loss. So the nutrient calculator hopefully will provide growers with greater certainty that they can make nutrient reductions and provide better environmental outcomes without any risk of yield loss. So yeah, I'd just like to thank the grower cooperators who've been involved in the project for making their properties available, and just like to thank all our collaborators who've been helpful in generating the data that's going to back this calculator. Thank you.
Excellent. Thank you, David. And we might launch straight into questions now from you, our audience. So as I mentioned earlier, feel free to type those questions in on your control panel and they'll come straight through to me. We've had a couple come in so far, and I might just put that perhaps to David and Scott in the first instance, just a question about the calculator itself. What are the timelines for the development of that calculator and app?
Yeah, thanks, Carl, and can't see that question, but yeah, good question. So we're hoping the project runs for another 12 months. So within that 12 months, we should have a beta version out. We've been a bit delayed with the testing of some of the more user-friendly aspects of it, I suppose, due to COVID issues. So we are running a little bit behind, but within the next 12 months, we should have a beta version where we'll be looking for guinea pigs to basically. We really want to hammer on the usability of it. So we don't want to produce something that's too complicated or not user-friendly or not displaying the relevant information. So we do want to go through a pretty rigorous consultation program, which should be starting within the next 12 months.
Great, thanks, David. Another question we came in, which relates to your final slide, David Richards, was just your point around different amendments supplying different nutrients in terms of the type of organic amendment, in terms of the feedstock. Does it also differ in terms of the form of that product, palletized versus not palletized, and other forms?
I guess we haven't really done experiments with these products at the moment, but we plan to. So the pelletization process is probably going to have other benefits, I guess, in terms of making a more dense, easier to transport product. So, but in terms of how they release nutrients, we don't really have a lot of data on that at this stage, but it's certainly something we'll be looking at in future trials on this project.
Yep, thanks, David. Another question that's come in from Isabel, thanks Isabel, was just a question around what factors of yield improvement were looked at. Was it mainly size, or were there other factors like firmness, flavour, nutrient content uniformity considered as well.
Okay, so it's mostly been, yeah, looking at the actual yield, so really size, but we have had a quality assessment done of the celery crop by the farmer. We just haven't got that data back yet, so we need to chase that up. We have looked at that in our past trials too in celery. Yeah, we're happy to do it where there are sort of defined quality criteria that we can assess against. Yeah, it's just knowing which metrics to use in the assessments for whatever particular commodity.
We also looked at it in Queensland at a different trial as well. So in lettuce and broccoli, around, so yeah, those marketability traits based on Woolworth specifications. I can't remember the exact results off the top of my head, but certainly I believe with the organic amendment products, the maturity window was much narrower, so it actually was quite useful in terms of just getting in being able to harvest it and get that size range much closer. So there were some additional benefits as well, for sure.
Thanks, David. Ian, you were going to jump in as well.
I was just going to say, we have looked at storage in a few trials, and there's been no negative effects of the combined treatments, which is important. And so just leave it at that.
Thanks, Ian. David Richards, you were going to just provide an additional point there as well.
I was just going to say, yeah, we look at nutrient levels in the crop, primarily nitrate. So I'm not sure if it's in Australia whether it's a concern of high nitrates in produce, but yeah, that could be a quality parameter that buyers might be looking at.
Thank you all. Another question that's come in from Jose was just asking, wouldn't it be easier to elaborate the extraction curves for the crops using the missing factor technique? Any comment on that would be appreciated if possible.
Who's that one directed to?
We can just put it more broadly to the group if there were any comments, but if not, we can take that offline if you wanted to.
Yeah, I'm not familiar with that technique.
No, that's okay.
I suppose, yeah, once we sort of start to get a bit more of an understanding of how some of these responses work, certainly filling in the gaps, we can incorporate a number of different techniques, including sort of simpler modeling techniques. But I suppose at this stage, you know, it's really around just the diversity of products we're looking at and the diversity of crops. We sort of really need those sort of fundamental data sets, I suppose, so we're not looking at every single thing, obviously, in the field, any combination. We're sort of selecting ones which will fill sort of the widest range of baseline data. So that's why we're sort of comparing a very diverse product, such as a urban-derived compost versus sort of pretty available animal manure. So we can fill the gaps using other techniques, absolutely.
That's great. Thanks, Dave. Ian, you mentioned earlier just some of the international examples of where Europe and other jurisdictions had capped the annual use of nitrogen. I was just wondering if you could speak briefly to how that played out in practice in Europe and how that might translate to somewhere like Australia.
Thanks, Carl. Look, the policy in Europe is there. The countries have to report every 4 years on their performance against it. It's a big stick type of system, but the stick never comes down on your back. So it's there to manage nitrate, to have surveys in streams and surface water, and set limits and a whole range of factors on different manures. And I think eventually that will come into Australia. I know there are certain meetings coming on in the near future that we'll be looking at that. But I think if we go in with a very positive approach to those, realising that there is a bit of a margin for improvement, we can meet those requirements that Europe is doing as well in certain regions, and in others they're not. And where they're not, they're having to implement regulations and policies that can get them closer to that. And there's lots of exciting science out there. I know Dave said there are not many that we've looked at. We've looked at a few that we probably can't talk too much about, but we know the companies are interested in this aspect as well, and forwarding those products onto industry to make use of nutrients better, particularly nitrogen.
Thanks, Ian. And look, one of the exciting things with this project still underway, obviously with the app under development, we were really keen to get your feedback on the line around your level of interest in evaluating a draft of the Organic Amendment app and providing some feedback to the research team on the line. If you'd like to just click one of those options there, if you are interested, we can make sure we follow up with you after this session. If you would like to continue to be involved, we've got a couple of you that have voted, about half or so. So I might close that poll back off and just share my last slide here. So we've gone just on the hour now. We'd like to thank you for joining us today, but also thank our panel of presenters from Queensland University of Tech and La Trobe. If you did want some further information and resources, there are some webinar recordings, some fact sheets, some case studies available online, and as I mentioned before, some handouts on the control panel on the side of your screen today. Please feel free to get in touch with our Regional Development Officer for VegNet in Victoria, Dimi Kiriakou. Her details are up on the screen, and we can make sure we connect you up with the right information and the right people as well. So without further ado, thank you very much, and we'll keep in touch. Bye, everyone.
Thanks, all. Thanks, Carl. Thank you very much.
Thank you.